Today, our topic of discussion is reinforcement learning, uh, one topic of Unit 5 of machine learning. So, what we are going to cover in this particular lecture are introduction to reinforcement learning, what the learning problem is, what are different issues in reinforcement learning. When we talk about other methods of machine learning, those are our supervised or unsupervised. Then we'll talk about the reinforcement learning using Markov decision processes. There are so many ways to do this. We'll talk about here. We will in this particular lecture. We'll talk about Markov decision process, and then we will introduce the Q learning. So first point is, what is reinforcement? What is the reinforcement learning? What it talk about? The reinforcement learning addresses the question of how an autonomous agent that senses and acts in its environment can learn to choose optimal solution to achieve its goal. So what we are talking about, an autonomous agent is there. Totally autonomous means the agent is doing its actions, its own, deciding what to do. Now the point is, it is working in an environment. There is a task environment where the agent has to work. So when we are talking about this, then what is to be done? The agent will itself learn. What it will do? It need to do some work, so it need to achieve some goal. So to achieve that goal, what is the optimal action that should be taken? So the choice of these optimal actions are to be decided. So that is reinforcement learning problem. Each time the agent performs an action in its environment, a trainer may provide a reward or a penalty to indicate the desirability of the resulting state. Okay, so what does it mean? It means the agent will do something. What agent is doing? Agent is learning on its own. So how will it learn? It will learn by doing actions. When it will do some actions and it will get something in return, that can be a positive reward or negative reward. So negative reward here we are referring as penalty. So it will get a reward or penalty. So the agent will itself come to know that the wrong action has been taken or a correct action has been taken. So what we are talking about, when training an agent to play a game, the trainer might provide a positive reward when the game is won and a negative reward when it is lost. And when it is in some other state, then zero reward. So the positive reward will tell that something is correctly happened or rightly done, and negative means something is wrongly done or not desirable. Okay, and zero reward means it is not having any effect. The task of agent is to learn from this indirect delayed reward. The reward is delayed means firstly we are doing the thing and then we are getting it. Okay, the task of the agent is to learn from this indirect. Why we are saying it? Because the agent is perceiving something from the environment. When it is perceiving, then it is coming to know that it has achieved or not achieved the goal. So if it is moving towards achievement of the goal, we are taking it as positive reward, and otherwise we are taking it as negative reward. So we need to choose sequence of actions that produce the greatest cumulative award. It means when a goal is to be achieved by an agent will do some action, then another action, and finally it will reach to the goal. So when it is doing the first action, it gets something, it may be reward, it may be penalty. Then on second again, it is getting something that may be reward or penalty. And finally, we have to see the cumulative reward. This is our environment. When we are talking about reinforcement learning problem, so what is there? The task environment in which the agent will work and the agent. What is the environment? What is the problem? Agent is interacting with the environment agent is doing actions in environment, okay, and as a perceiving, it is getting as a result reward, and when it do some action on the in the environment, the state will get changed. So agent is in one state, then it will do some action, it will be in another state. Okay, so let me take some initial state S naught, and this is one possible action in S naught which has been taken here. Okay, so if as in S naught state the action taken is A naught, then what agent will get? It will get R naught reward and will move to next state, that is S1. So what is it is taking as from the environment? It is what it is giving to the environment. It is acting, so it is applying action, and as a result, state is getting changed of the agent, and agent is getting reward. So in this state, when this action is taken, this is the reward, and this is the next state. Now, what is next state? S1. So now current state is, let me say, S1. Now A1 is one of the possible action. When agent will do A1 action in S1 state, it will get R1 reward, and the next state will be S2. Now in S2, another action. Okay, so what will be reward, and so on. That is our scenario. So what is our learning problem? An agent is interacting with its environment. It exists in the environment described by some set of possible states. S0, S1, S2. These are the possible states shown here. Same way we are having others also. It can perform any of a set of possible actions. There are few possible actions, so any among these can be performed. Each time it performs an action AT in some state ST, the agent receives a real value reward RT. In S1 state, doing action A1, it is getting the R1 reward. So that is RT. That indicates the immediate value of this state action transition. When from this state with this action, this state transition occurred, then this is the immediate value that the agent is getting. This produces a sequence of states SI, actions AI, and immediate rewards I. So this is what is the sequence? S0, action A0, reward R0. Then S1, state action A1, reward R1. Then state S2, action A2, reward R2. Okay, so that is the sequence. Now, what the problem is? The agent's task is to learn a control policy by S2A, means states this action that maximizes the expected sum of these rewards with future rewards discounted exponentially by their delay. So what is the thing to be done? We need to learn to choose actions that maximizes this cumulative reward. What is this cumulative reward? First reward is R0, then gamma R1 plus gamma square R2. Okay, this is discounted exponential. This the R0, R1, R2, R3, these are the reward. Gamma is a parameter between value 0 and 1, which we are calling here discount. Okay, so what is the thing? It is a discounted award that is to be learned. That is our reinforcement learning. Now, as we discussed on last point, what we have to learn? We have to learn the policy which is maximizing the reward. Which reward? Cumulative, discounted cumulative. Okay. The problem of learning a control policy to choose actions in some respect to function approximation problems. as we have seen in other methods, like if I talk about classification. So what actually we are doing, we are trying to find out a function which approximates our available data. So it is in some respects similar to that. But what here is, here the point is the target function to be learned is a control policy. Here we are learning the control policy by S2 is set of states to set of actions. From these set of states, what actions we will perform to get the maximum reward. That a policy that outputs an appropriate action from a set of A given the current state S from the set S. Okay, so that we have to learn the appropriate action. So what we need here, we can say that the control policy that we have to learn, that is something like target function. Now what the points are, we must learn how to decide the policy, which policy which is giving us the best cumulative award, maximum cumulative award. Okay, so if we do it like function approximation, then what are the challenges we will have? Is it same? So we should understand how to take that. This differs from other function approximation in several important respects. There are so many aspects what we have to go through to understand this control policy learning. How can we take it like a function approximation? So here we are going to discuss few points that should be taken here. These are the problems with reinforcement learning, that is learning control policy in comparison to target functions. Okay, so what the point is, the main point, we are getting delayed reward. Why we are calling it delayed reward? If I talk about machine learning, in supervised machine learning, there is some data training examples are given with target. Okay. In reinforcement learning, the training information is not available. The trainer provides only a sequence of immediate reward values as the agent executes its sequence of action. Only the sequence of reward value. Firstly, it is getting R0 reward, then it is getting R1 reward and R2 and so on. Okay, so we are having this sequence of immediate reward values when we are taking some sequence of actions. The agent therefore faces the problem of temporal credit assignment. Means determining which of the action in sequence are to be credited with producing the eventual reward. As we are getting the reward sequence and finally we are taking the cumulative. Okay, so here the problem is to which action we should give the credit and to which and of which the credit is lesser. That is a problem that we need to see, because we are not given any training data. We are given sequence of rewards and actions. So if some action has given us the actual credit, or that action in combination of previous has given us some action and so on. So it is very tough to decide. Exploration, a very important aspect of machine learning, and that aspect of reinforcement machine learning. The agent influences the distribution of training example by the action sequence it chooses. So we are given some training examples in supervised machine learning, but here we are talking about reinforcement. So the agent is working in an environment and is doing actions. Now these actions are collected as examples, that we have done this thing, then we got this. Okay, so the training is influenced by the action sequence the agent is doing. Okay, so when the training is depending on the actions of the agent. Now the point is the question, which question? The question is, the learner faces a trade-off in choosing whether to favor exploration. It means working in direction of unknown states and actions so that new information can be gathered, or exploitation of states and actions. Means which we have already learned, we get the maximum of that. Okay. So, or exploitation of states and action that it has already learned with will yield high value. That is to maximize the cumulative reward. So that is one problem the agent faces. What is that? Exploration should be taken or exploitation. Exploration will give us new examples, and exploitation will give the maximization of the already already executed examples, already uh, done the action sequence and the reward taken. Another problem that agents have here, that is partially observable stimulus. The agent can perceive the entire state of the environment at each time step. In many practical situations, the sensors only provide partial information. Okay, for example, there is a camera with an agent, the robot. The robot is capturing the images in front of that. Okay, and if it is not having the back camera, it is not able to see the uh, picture, that is the environment which is behind that. For example, a robot with a forward pointing camera cannot say what is behind it. In such cases, it may be necessary for the agent to consider its previous observation. So now, because there is no previous camera, so agent will link the previous observations, that what it observed previously, so that it can have a guess that what may be behind, or what may other thing be would be present in the environment. Lifelong learning. Unlike isolated function approximation tasks, robot learning requires that the robot learn several related tasks within the same environment using the same sensors. What the point is, a mobile robot may need to learn how to dock in its battery charging, how to navigate through narrow corridors, how to pick up output from laser printers. Okay, so many things are there that the agent needs to do. Several related tasks. To do something, it must be charged. So it has to see how to put on battery charger. This setting raises the possibility of using previously detailed experience or knowledge to reduce sample complexity when learning new tasks. It means it is when it is working in some domain, it needs to do many related tasks. Okay, so to pick a laser printer output, it needs to move through corridor, and to keep its battery charge, it needs to dock itself onto the battery charger. So these are the related tasks that the agent needs to do. So for all these, because it has to need what agent is doing, agent is taking the output. So agent needs to keep track of how to move to that direction. So what we are doing, we are learning, we are making the agent learn, reinforcement learning. In reinforcement learning, the agent is learning after working in the environment. It is performing some actions, getting some rewards and penalty, and then deciding the best policy. That is our work. Okay, so when we have to do this learning, the learning task, there are many ways to do this. Okay, there are many possibilities. For example, the action could be deterministic or may not be deterministic. The agent can predict the next state that will result from each action, or it may not be. Okay, so these are the different ways to learn. I should assume that it is deterministic, or I may there is another possibility that it is not deterministic. Okay, the agent is trained by an expert who shows it examples of optimal action sequence, or it must train itself by performing actions of its own choice. There is some expert who is providing the basic information or not. Okay, so prediction is possible or not, it is deterministic or not, means after doing one action, only one state is coming in output as next state, or maybe possibility of two. Okay, so that is the concept, that so many possibilities are there. Okay, when we are trying to understand the learning task of reinforcement learning. So what we are going to consider in this particular slide, that is Markov decision process. So now let us talk about Markov decision process. Okay, so in Markov decision processes, what we are having, we are assuming that we are having finite state of a set of states, that is S, finite set of actions, that is A. At each discrete time, agent observes ST state belonging to S and chooses action AT. So there is some current state of action. So agent knows, observes what is the current state and what are the available actions. From that, it will choose an action AT belonging to A. Then it receives immediate reward RT, and the state changes from ST to ST plus 1. At Tth time, the state was ST, and now after doing the AT action, it will get the reward RT, and it will get the state change to ST plus 1. Okay, so Markov decision processes are in ST, when action AT will be taken, the next state will be ST plus 1. So we are taking delta as the function here and R as the reward function. Okay, what is the reward function? In ST, state ST, when we will do action AT, the reward received will be RT. So here RT and ST plus 1, these are the outputs, depend only on the current state and actions. This is Markov assumption. What is Markov assumption? Markov assumption says that the reward and the next state, that depends only on the current state and the action taken. Function delta and R may be non-deterministic. Here in this Markov decision process discussion, we are taking it as deterministic. We will talk about deterministic. And functions delta and R are not necessarily known to agent. It may be known to agent or may not be known to agent. So we are talking about Markov decision process. So what is the agent learning task? So what we have to do, the agent, what the agent has to do, the agent needs to learn action policy by from S to A that maximizes the cumulative reward. Okay, so we are taking here expected cumulative reward. RT plus gamma, RT plus 1 plus gamma square, RT plus 1 and so on from any starting state in S. We are having set of states. From that set of states, there will be some starting state. Starting from there, we need to optimize this cumulative reward, and we will choose that policy that will maximize the cumulative reward. And what gamma here is actually discussed on previous slide, one of the previous slides, that it is between 0 and 1, and it is discount factor for the future reward. Now, what important here is, we are having the target function, and the target function is the policy from S to A. Okay, but what else is there to be noted? There are no training examples. We are not having training example of the form that there is set of state, state S and action A. What we are having state S, action A, and after taking this, we are getting reward R. This is the data that we are having. Okay, what we are having for this state, this action will get this reward. This is our data that we are getting when agent is working in the environment. So we are considering here deterministic one. So for each possible policy file, the agent might adopt, we can define an evaluation function. So what we need here, we need to evaluate the states. So we will define a evaluation function on the states. So we are taking that as value function V pi S. This is the evaluation function under policy pi. If I assume I take pi policy means from this state I'll take this action. Okay. So I'm taking the cumulative reward as the evaluation function. What is cumulative reward? RT plus gamma RT plus 1 plus gamma square RT plus 1 and so on. RT plus 2 and so on. Where these are the rewards when we start at state S with policy pi. Policy pi is telling us that from this state, take this action, go to this state. Then take that action, go to next state and so on. So we are having different possibilities. Now, what we actually want. This is our policy, one policy, and this is evaluation value of that. The evaluation function will tell us what is the evaluation value of that, what is the fitness value of that. Okay, now what is desirable? The desirable is the task to learn the optimal policy pi star which maximizes this value. This is the fitness value, the evaluation value function result. This evaluation function result must be higher, must be maximum. That is our that will be our optimal policy. Now, how can an agent learn an optimal policy for an arbitrary environment? It is difficult to learn the function because the available training example doesn't provide us training examples. The only training information available to the learner is the sequence of immediate rewards. Given this kind of training information, it is easier to learn a numeric evaluation function defined over states and actions than implement the optimal policy in terms of evaluation function that we were talking about. Now the point is, what evaluation function? We are saying that we can design it. Now what evaluation function? Okay, so if we take the evaluation function value of S1 state and evaluation function value of S2 state, okay, so which will be better, which choice will be better, in which the agent should prefer state S1 over S2, where the evaluation value of S1 is greater than evaluation value of S2 state. We will consider the evaluation functions of different state. If I start with S1, I get V star S1. If I start with S2, I will get V star S2. So, when I will prefer S1, when that value for S1 will be greater than that of S2. The agent policy must choose among actions, not among states. Now the point is, we are talking evaluation value of the state. What is S1, S2? We are talking about S1 and S2, the states. But actually what we have to decide, we have to decide the action, the choices of actions. However, it can use V star in certain settings to choose among actions as well. So now we will use that for actions. The optimal action in state S is the action A that maximizes the sum of immediate reward SRSA plus the value V star of the immediate successor state. Now, as we are given the evaluation value of states, but we have to choose the action, so we will see the successor state evaluation value. So we will select that action that maximizes the sum of this reward plus evaluation value of the next state. Okay. So we will use the term look ahead search. How can we do it? We can do it with look ahead search. So what will be the best policy, best action? What will be the best action? We will take that action which maximizes reward RSA, means when applied to S, it will get some reward, and the next state will be delta SA, the evaluation value of that. Both things will be considered. What reward we are getting here, okay, and what will be evaluation value of the next state. We will see both the things, reward as well as the effect, that is the fitness of the evaluation function value of the next state. Okay, so now the point is this works well if agent knows delta as well as R. But what will happen if it doesn't know the functions delta and R? So because delta may be known or may not be known, R may be known, may not be known in advance. Okay, so that's why we use here Q function that gives us Q learning. We define a Q function of state S with action A as the reward that agent will get by performing action A in state S and the evaluation value of the next state. It is similar to our evaluation function. Okay, so what we will do now, then we will select that policy that will maximize this Q value. Which policy we will take? Which is taking this, which is optimizing, giving us the maximum value of this Q function. Now we were talking about delta and R unknown, but here again we are having the same functions when we are talking about delta. So what we will do, we will define it recursively. What is QST AT? It will be reward when AT will be performed in ST, current state, and evaluation function value of the next state. What will be evaluation value of the next state? The maximized Q value from the given possible actions. We are given some actions, we'll perform that. Okay, so what will be the evaluation value? That will depend on that action which will maximize this value. So what is done here? QST is defined as a recursive function in terms of QST only. Okay, so what is QSA? It will be R, that is reward, plus discounted Q value of S dash, the next state. Result. S dash is resulting state. Q value of S dash, and the action from the possible actions which is maximizing this Q value. This is our training rule to learn Q. So we took the Q function value, and what we did, we defined it recursively in terms of itself. So now we are not having our known delta function. What will be next state? That is not known to us. So this is Q learning algorithm, and as we discussed on one of the previous slides, that we are talking about deterministic world. If S state, and in S state we do action A, then the next state is deterministic. It is not non-deterministic. Okay. So what is the algorithm? For each state S, a initialized table entry QSA 0. All the initial entries will be 0. Observe the current state S and do forward. It is lifelong learning, reinforcement. Go on improving. Select an action A and execute it. Receive immediate reward R. Observe the new state S dash. Update the table entry for QSA as follows. That is R plus which Q value, which is giving us the maximum reward, and that will be our next state. See this one, the robot is here. It is deciding the action. Now what will be there? How it is deciding the action? We are given possibilities we are having if we take this next state. So what is this next state? This from here we are having 3 possibilities. In this direction we will get 63 reward. In this we will get 81. In this 100. Now what action I should take? Move left, move right, or move down? Which action I should select? Which is giving us maximum possibility, maximum Q value. Okay, so here gamma we have taken as learning, that is 0.9. Next off, what are the possibilities? 3, 63, 81 and 100. These are the 3 possible values for this reward. Now which we will take? Which will give us maximum? What is maximum? This one, 100. Okay, so what we have taken? 100 here. 0.9 into 100 and reward we have taken here 0. So 0.9 into 100 plus 0, 9. So which we have selected, which is maximizing this Q value. So in this way we will go on updating the Q function. That is our Q learn. So in this particular lecture we talked about reinforcement learning. Then we talked about the problems that are present in reinforcement learning in comparison to example-based learning like supervised. And then we talked about Markov decision process, and then we introduced the Q function. Thank you.